Let me start the recording again. Okay, so this is the topics for discussions today. We'll talk about the minimum iterator requirements, although we mentioned them before, but we'll reiterate today. And we'll talk about the lambda expressions. This is something new to us, but it's widely used, so we should be aware of those. We'll talk about the algorithms and finally about the function objects. I cannot guarantee you that you will be using them like every day, no, but you might be using them. So that's why we are covering them. That was Python stuff only, no. Okay, and we are kind of having a general class. So we do review some things, we don't deep dive too deep, and you will see it today, me mentioning it again. And but we definitely touch the topics that you might encounter when you are working with C++ or any other language, to tell you the truth. So the standard library separates algorithms from containers, with some exceptions. And the separation allows to add new algorithms and to use them on different containers. Now, we discussed in the previous class that iterators are implemented for each type of the container, right? And that the type of the iterator defines which algorithms can be applied to the container. So this is important, the algorithm, for the algorithm. So if an algorithm, for example, requires forward iterator, right? Then that algorithm will only be able to operate on the containers that support forward iterators, or maybe bidirectional iterators, or maybe random access iterators, right? Or all of them together at the same time. So, obviously, these do represent our requirements from the side of the algorithms to the iterators, right? Now, since iterators simply point to container elements, right, it's possible for them to become invalid. So we do have these cases where the iterator invalidation happens. A good example here would be if we call the clear method on a vector, it means that its all elements will be destroyed, right? And any iterators that are pointing to elements here or there or somewhere else will be invalid now, right? Now, if we discuss the insertion and deletion operations, so here I'm talking about the insertions and here I'm talking about the deletions or erasing operations. When can the iterator invalidation happen? So for example, if we have a vector, right, then if the vector is reallocated, all iterators are invalidated, right? If no reallocation happens, then, but we have the insertion, right? Then the iterators from the insertion point to the end of the vector are invalidated because we are inserting the elements there. So the elements are shifted, right? So the previous pointers, the previous iterators are invalid anymore, right? So for the DQ, when we insert an element into it, all iterators are invalidated. For the list, we discussed with you, but we didn't do the forward list. We only did the list example, right? All iterators will be valid. Now, for the ordered associative containers, all iterators will remain valid. But however, for the unordered associative container, all iterators will be invalidated, right? In case if we have to reallocate the container. And by reallocate, I mean we ran out of space, right? So we have to do resizing. So then in this case, when the resizing happens, it's the same as for the vector, right? So we will, all those iterators will become invalidated. Now, when we are erasing or deleting, right, from a container, iterators that are erased, of course, become invalidated, right, if iterator is pointing to that element. And in addition, for a vector, the iterators from erased elements, right, to the end are invalidated because the element is removed from the sequence. So the shifting, right, all the elements to the right of it will be shifted one position to the left. So then we have an issue. And then in the DQ case, if an element in the middle, of the GQ is erased, then all iterators are invalidated. So we don't have any issues if the element is removed from the end or from the front, right? But we do have issues if it's somewhere in the middle. Okay, so this is kind of just noticing it. I don't have an example when we like really run into this situation. We just usually just keep it in mind in case if that happens, right? So let's talk about the lambda expressions. You probably noticed, maybe not, but just reminding you in this case that many algorithms from standard library can receive a function pointer, right, as parameter. Because function name is easily convertible to a pointer, right, to that function's code. So whenever we are writing a definition of the function, if I refer to it by name without the parentheses, right, without the parentheses, it's a pointer to that function's body, right? So before we can pass a function pointer to an algorithm, of course, we need to declare it, right? You'll see the examples today. Now, starting from C++, standard 11, we have another convenient notation to use. It's like a shorthand notation. We could use lambda expressions to do that. We are creating functions that don't have names. We call them anonymous functions, right? So it doesn't have a name, but it is working. It is a function. So they could be used instead of the function pointers in the place of the function pointer. And we do have an example, so I'll show you where we could do that. I just hope I won't forget to create a function as well. Okay, so lambda expressions, or simply lambdas, are defined locally inside the functions, and they can be used to manipulate local variables of the enclosing function. So the function that has them in them, those lambdas can use the variables that are defined inside this function. We will call it capturing or closure. Okay, so here is a general syntax that I grabbed from the web page. I think it was CPP reference. And now what we will mostly be using today is this syntax. So it kind of consists of 3 items. So let's talk about them first. I'll mention some of these, but not all, because then it goes too deep into details, and some of them we really don't understand yet. So whenever we use the square brackets, even if they're empty, right, it's called lambda introducer. So it kind of introduces the lambda notation to us. Now, if something is listed inside, we call them captures, right? Now, what it does is it captures the local variables from the function, right? So once again, it's not necessary to do this capture, and we can easily keep it empty. So you will see the examples where we have something there and when we don't. Now, then we come with the list of the parameters, right? This is what the function is called on. Like imagine we would have the regular function, right? It has the list of arguments, the list of parameters. That's exactly the same thing, right? So some parameters will be fed into this lambda, right, expression. Now, what we could do there is we could auto-deduce the type of the parameter. So its type will be inferred by the compiler. And you could see me using it more and more now, right? And if we use the order, then we say that this is a generic lambda. So it has like a special name, generic lambda, right? And it was introduced from the C++ standard 14, so 2014 year standard. Very handy. To tell you the truth, this order is really, really handy, and you will be seeing me using it a lot today. Now, the body is the body of the function, right? So this is the list of the parameters. This is the body of the function. Here we will be doing some stuff, right, to the parameters and maybe to those captured variables from the enclosing function, right? Okay, now this is a more extended list of things that could be added into the lambda. So for example, this is since standard 2020. So, I don't even know that many details about, but since we did talk about the template functions, right, it's probably worth mentioning them here. So we have an option of adding optional template parameter list, right? And if we add them, then we might put some specific constraints on them. So we will put them over here. Right? So it's, once again, since the 2020 standard, and I'm not going to give you any examples for that. We're not going to use it, but just so that you would be aware that, you know, what we're using today, it's just this tiny, not modified, but kind of the one of the most condensed forms of the lambdas notation there. Okay, now you probably can guess that the exceptions, you know, maybe the list of some exceptions that might be directly or indirectly thrown, right? And then red is usually the return type. Now, what you will see today is if it will not be present, we will not announce it. And what will happen in this case is it will be applied by the function return statements. So it could be void, right, easily. Dale, I don't know t-params. No, this is not the header. T-params is not a header. These less, you know, these things say that it's optional parameter. It's not the header, right? It's not about the header. And I'm not sure that we will be able to use the header there. I doubt, you know, I doubt it. That'll be just a list, yeah. So, but it's not a header. Okay. Now, so this is what we will be playing with, and I do have an example for that. And since, you know, I still remember about it, I just wanted to show you how will it look like with the function as well. So let me switch to the full screen sharing because I don't think that I still have it. Yes. Okay. And I'll switch to the Visual Studio. Okay. So this is what I do. I'm going to play with the vector. I did notice that the majority of the examples from the book, they work with the C++ style array. Okay, it's because we have the iterators there for the beginning of the array, for the end, and so forth. But I prefer to work with the vector because you were also asked to study the information about the vectors, right, from the previous chapter. So it's good to kind of review them, and especially in terms of the output. So we'll do that trick today. So, but a little bit later, I think. Yes, a little bit later. At least I don't see the outstream here I'm using. Okay, so I am including the library input output stream because we usually include it for the input and output. I am including the algorithm because this function will be used by us for each. So we will talk about it for each, right? Because we will be using that one. And I include the vector because we are using a vector here. So I'm creating a vector of integers, 10, 20, 30, 40, 50. These are the elements of the vector. And then I am using this variable sum because I would like to add them all up. And I will be using the lambda notation for it. The lambda expression will do it for me. But the first thing I would do with this lambda expression is to just display out the elements, right? Show what are they. Now, it might look weird to you, but you know, whatever it is. So for each, it's an algorithm. You could call it a function, but we call them algorithms. They work on containers, so we do prefer the name of the algorithm. So it's an algorithm which will call a function, and this is the function. It comes in the third place. It's the third argument of the for each call. So this function will be applied for every single element starting from this position and ending with this position, but not including it, right? So like it's, you know, it's like our indices in the Python, right? You remember in the square brackets, the last one was not included? Yes, but here just remind ourselves that the end is an iterator pointing to the place after the last element, right? So that's how it signals us that we don't have any more elements, right? So this will return as an iterator, right? And you could see it from this explanation, iterator, right? So this will be an iterator pointing to the element. It's not even an element, it's like a place right after the last element, right? So now check out this lambda expression, right? So here I'm introducing the lambda expression, the capture, which is empty, right? Then I say, this is the list of the parameters. Now, where will it get them? Where will it get them, those parameters? The for each will provide it. So it will grab each element in this interval and it will provide it as a parameter, as the argument to this lambda expression, right? So I said auto here. So it will automatically inherit the type of the element which is grabbed over here by the algorithm for each, right? And we could deduce that it will be int. So I could put int here. It will not do any damage, but since we would like to keep things as general as we can when it's possible and when it's easy, we do prefer to use the auto term here. Okay, auto specifier. Okay, now this is the body of the function. I could easily move it to the next line. I can make it several lines of code. It's a body. It is hidden here. It looks weird, but it is a body. So feel free to put more than one line of code over here. Now this code is extremely silly and simple, right? It will see out the value of the item and it will go to the next line, right? So let me comment everything else over here just to show you how it works and what do we see. Okay, just to show you how it works, right? Okay, so over here, right? These are our elements. The begin will return the iterator to the very first element, right? Now the end will return pointer over here, right after the 15. Now for each of this element, it will be supplied to this lambda expression, right? Now the type is deduced automatically. The cout function knows how to behave with the integers. It just displays them and goes to the next line, right? Now I, of course, could easily change it by replacing it maybe with the comma, right? It will probably look silly a little bit because at the end, then I will have to add, to make sure that we go to the next line, we'll have the comma at the end, right? But it looks nice. So I do use this style for a lot of our outputs today, so as you will see. Okay, so to me, it looks nicer just in case if the numbers are weird with the decimal points, huge, and so forth. So like to use the comma, right, with the space. But this one is absolutely, completely up to us, what we decide to do. Now, what we can also do is we could add up the elements. But what we will have to do that, and you see I use this variable sum over here, I'll have to capture it by the lambda, right? So I'll have to have an access to it to be able to modify it through the lambda expression. So what I do over here is for each starts with the same beginning, right? The first two parameters. But this lambda expression is capturing the local variable of its function, right, where it is defined. So it's getting the access by reference to the sum. And what it does inside its body is that it's adding each next item to the sum, right? And here we could see, what is it? Like, what's the value of the sum now, right? So over here, I'll comment out the rest, right? So we captured the local variable sum for our lambda expression. It is using this one as a parameter, which is provided by the for each, right, from this range. And it's adding all those items to the sum, right? So every time for every item, the sum will be modified. So let's run it. We can capture more than one variable, right? We'll just use the comma there in this case. So here is the sum of all elements. Assuming that it's true, yes, 40 plus 10 is 50, so it's 100, 150. Yes, that's a correct, right? One. Okay, now what else can we do? Since we can display them, why can't we display them multiplied by 3, right? So over here, what I do is I display those values, but I multiply them by 3. So this C out, let me move it to the next line so that you could see it nicely. Instead of the item, I just do times 3. You see what will happen here. The items themselves, they're not modified, right? Because I'm doing here it by the value. And if I wanted to do, I wanted to be more safe, I could even say C begin and C end, for which will allow me to do it. Now remember C begin, it means that we have a constant iterator. Now what the constant here means is that the iterator is pointing to a constant value that cannot be modified, right? So this is what it means. It doesn't mean that the value of the iterator is constant. No, it's pointing to the constant value, right? So this is just to make sure that the items are not modified themselves, right? So if we run it, here are our values. So 10 times 3 is 30, 20 by 3 is 90, 30 by 3 is 20 by 3 is 60, 30 times 3 is 90, and so forth, right? We can see that indeed they were multiplied. Okay, now what I could do, before we proceed, actually, yeah, the multiples. Okay, let me show you the pushback. Oh no, this is for your assignment. Okay, so what I could also do is I could actually replace this one with a function, right? So easily. Now, how about doing the following? Will I have it in the example? I will, I'm just thinking of maybe I'll have it in another example and then I will show it to you. I'll have it in the example. Okay, I'll have it in the example. Yeah, let's do it like step by step. I'll have it in the example, or maybe while you're working on the example over here, I can show you what I could also do. Now, what I want to demonstrate you right at this moment, let me check the chat messages. What is the C begin? So yes, that I explained, right? What the C begin is. Okay, now what I also want to demonstrate to you is, so here I'm providing the lambda, but I could just give the name of the function there, right? And it will be called and it will return the value to me. So let me show you first your assignment for self-practice. Okay, so Venkai's question, right? Why do we use the reference to the sum? Because we are modifying it. And now if we don't modify it, let's try it actually. So I used it because I'm going to modify this value, right? So I wanted to make sure that it is captured and then I capture it by reference, right? So let's try it. The error list. Okay, yeah, you see, it even tells me. So a copy capture cannot be modified in a non-mutable lambda. Okay, so then you know what, I can do it. I could use those expressions. I could say that it's a mutable lambda. So there are these ways to do it. I just didn't mention them before, so I don't want to use them. But it's possible to say that this lambda is mutable. Okay, so, but here once again, so in order to be able to modify it, I had to use it by reference. Questions? Okay. So let's put it back. Let's put it back. Okay. Now, here is my assignment for you to work a little bit on lambdas, right? So I'm going to push more values into it. So push 60, 70, 80, 90, and 100. Now, what we would like to do is to display only the multiples of 3, but by using the lambda. So we would use the for each function. I would like to use it with the C out. And once again, keep in mind, this is the body of the functions, so I can put a good chunk of code there, right? Like ifs could be there and so forth. So what I'm asking you to do, and I will pull this one down so that you could see this one and this one as well, is to grab a piece of paper write the code that you think will work here if you were to put the code to display only the multiples of 3, okay? So take your time, I'll give you a few minutes, and then I'll type in the code, okay? Okay, so let me try work on it, right? You probably finished and you had an idea. Don't we have an extra parenthesis at the end, a line of the algorithm just after the curly size? So it says you're talking about this one, right? Over here. No parenthesis here. You see, this is an opening curly braces, right? This is the closing one. Now this parenthesis comes from for each. You see, right? So this parenthesis is for this one, and then we finish it up. Okay, so yeah, because of that, I am actually missing it myself all the time. So this is what I do. When I do for each, I immediately put the 3 parameters. So for example, I know that I will do my v dot begin, right? I can do c begin here, my v end, and then I will put the comma, I put the space, and I put this, okay? Just to make sure that I will not forget this parenthesis. Now what I do is I put the lambda expression in place. So I could do it like this on the next line, And usually what I do here as well is I do this, okay? So this way, I'm kind of set, right? I know that I need to fill out maybe this one, and maybe this one, but this I have to keep, right? So it helps me to not to forget those, this parenthesis. Yes. Okay, so let me erase this. Now I'm not going to capture anything, and I'm going to auto inherit the type of the item. Now, you know what, it will be a big body. So let me move it to the next line. And let's do the following. We need the multiples of 3. So it means that it should be divisible by 3, right? So I would say if this, also, once again, I'm afraid to, to use this one. So I will do it like this to make sure that the if's body is there, right? So if, what is it? Item remainder from the division by 3 is equal to 0, right? It means it's a multiple of 3. Then I will see out it. See out item, right? And I'll, I can put a comma there, right? Another thing, I regularly forget to put the semicolon here, so it happens to me because once again, I don't have it on a separate line, right? So when we do the lambda, we try to do them as compact as we can, right? So that it won't run out the screen, right? Overrun it. But we would like to keep them compact. So we do not move this one to the next line, this one to the next line. We try to kind of pile them up at the end. Okay, but let me check it out. So I'm going to see out the item if the division by 3 gives remainder of 0. And I'm going to put the comma there. So you know what I need to do at the end, just for the next iterations, right? For the operations, like what if I will output something there. So I'm going to add the and L over here. Let's try to do it like this. Okay, so what do we have here? Multiples of 3, you see them? 30, 60, and 90, right? 30, 60, and 90. Okay. Okay, something like that. Okay, now, you know what? I won't rewrite this one because we have a very similar one in the example at the end of the class, and I just want to make sure that we finish on time. So let me hold my horses and not to run and change, things here to show you some other. Okay. We can always use the normal method. That's not the point here. So the point here is to use the lambda expressions, right? They do seem strange and weird right now at the moment because we apply them to the things that we can do much easier, like Zubaru is saying here. So this code, I think everybody, right, can see the chat messages. So absolutely much more easier than what we see here. But the thing is, in order to understand the lambdas, you have to do them on easy examples. Otherwise, it will be so complicated and you just won't get the notion. Okay, so everything I'm gonna do today, and it's actually a good question, is something that we could do without them, right? So all the things that we're discussing is something that could be done much easier for us, right? Using the things that we learned before. But we have to learn some things that we could use in the future on much more complicated things where the use is really, welcomed. Okay, yes, but you're absolutely right. We could use much easier tools to do so. Okay, now let's go jump into the lecture slides. I'll have to raise it when I will be putting it onto our website. Oh, maybe put a comment there, right? Okay. This was this was practice. Okay, this was practice. Or maybe I'll put like a full code later on, close to it. Okay, I'll decide what to do best, but let's go back to the lecture slides and we'll talk about the algorithms now. Now, I don't know why my controls are not disappearing. It's weird. But at least it's working. Okay, so let's keep it that way. So we are going to use some searching, sorting, and a little bit else today. But once again, as I promised you, this will be just a tiny amount of everything that is listed in this chapter. So that's why I will be asking you to read section 16.4, which have the list of all the possible algorithms that are frequently used. Okay, but so let me go on, and this example we will be coding in real time because I would like to show you some things and to talk about them, instead of just simply going over them. Okay, because this also gives you a knowledge on how to start working on things. So I'm going to remove this one, remove, and I'm going to add a new item, and I will call it using algorithms. So the file that will be posted on our website will have a different name, but this one I will use to show you the work that we will do in class in real time. So as usual, we will include the input-output stream. We would also include the algorithm library. We will also include the vector because I'm planning to work with it. Once again, the book plays with the array. So instead of the vector, they are including the array. Okay, and then we will have to use the iterator. So that I will do for the output, include iterator. So I have to use it. So when I'm using, begin and end, I don't need to announce it. But when I am using some other things, then I have to announce them. So for example, for the output, I think it didn't allow me not to have this header. Okay, so in order to avoid all those names being listed, namespace, std, I'll just include the entire namespace. It's a huge amount of things, but just to keep our life easier. Okay, so this is the vector. I'm going to play with the integers because it's easy, and I will call it my v. Now let's do the numbers. 1, 7, just putting them in, right? Like this. What I want to see is the duplicates. So I want to have some duplicates because we'll try to remove them. So you'll see. Okay, and then maybe 17. So I have no idea what the size is, and to tell you the truth, I don't care. This will be taken care of automatically, but let me show you now how to use the iterator to output the entire vector to the display. So we will define output stream iterator. We will tie it to the cout, tie it to the cout, and we will say what it will be terminated with. Plus add the termination with, up to you. So we could use like 3 spaces, 1 space. The book is using spaces. I like to use commas. So let's stick to those ones, and you can choose it to whatever you wish. So let's announce the outstream iterator. It's on ints, right? Because the vector composed of ints. Let's call it output because that will be our output. And then this is what we will initialize it on. So as promised, cout and the terminating sequence, right, will be this. Okay, so I just initialized it here, right? Use the list initialization with the curly braces. Now, how to output it? We'll use the function copy. Well, okay, it's algorithm copy. So we have this copy algorithm. It comes from the algorithm. So copy, right, comes from here. And what it does is it copies some content. We give the beginning, check this one, first, last, and then the destination. So it copies all the elements into the destination. Guess what will be our destination? This iterator. It's funny, right? So if you already read that chapter, read that section that I asked you to, you saw this example. I believe they gave it there, but if not, then I'm showing it to you now. Right, so now vector, no, my vector, my V, right? So once again, what we try to do is we try to be careful. So if I'm not going to change the elements, why don't I use the const iterator, right? So my B, C, and, right? And if I'm going to modify something, then I will be using the begin and the end. Now the output is our destination. Funny, isn't it? We'll see all the elements now displayed. So I don't need to iterate over them. I don't need to put the for loop. Isn't it wonderful, right? So watch it here. I cannot bring it down because okay, let's do this. I'll bring it down and then I'll do this. Okay, it's my controls are glitching. So, okay, so check this out. This is the entire vector output, right? So 1, 7, 3, 5, and so forth, 17, right? All of them with just 2 lines, right? You could do 2 lines. The for loop, okay, it will also take 2 lines. So I cannot say that it occupies less space, but it's funny how it's done, right? It's funny, just how it's done. Okay, so we use the copy algorithm to output everything to the cout, right, to the display. Okay, let's try to remove some things from the array. And this was weird, to tell you the truth. I hope we will see the same weirdness here. So let's remove all. I wonder, is it all appearances? All appearances of, let's say, what, 7? We can remove all the, 5s. We have many of them. 1, 2, 3. No, let's do the 7. No, let's do the 5. Okay, let's do the 5. There's a 5. So we could do that by calling function remove. The function remove, actually, as far as I remember it correctly, but we could check it out. It removes all the duplicates, but not removes it from the vector. It kind of puts them at the end of the vector. So they're not like eliminated. It's weird. So, well, we can pull up the documentation of the remove. And here we're using it with the 3 parameters. So what the helper now shows me, it's about the file, right? But I'm not going to do it with the file. I'm going to do it on the vector. So my v begin. I'm going to modify things here, right? So, okay. And then my v end. Okay, and what to remove. So now finally, you see what I'm seeing here? First, last, and what to remove, right? So 5. 5 is to be removed. Okay. Now, it actually returns. What does it return? It returns a place. You know what? I think it's the returns the place to the new ending of the array. So we'll just Google it up. Remove, because I didn't put it up for you. So C++ remove. Now this one, remove. Let me just Google it like that. Let's see if we can find it. Okay, so this is it, right? This is reference for algorithm remove. That's what we're exactly looking for. So it transforms the range from first to last excluding into the range with all elements that compare equal to val removed and returns the iterator to the new end of that range. So that new returns me like the new ending, right? So we could try to use it, but I kind of want to see what's going on there. So we'll try to use the new ending for us. We will try to see the entire vector, what's going on there. So we'll experiment with it. Let's go back to our Visual Studio. So first, let's just display it, right, as it is. So Here, I'm just displaying it right away, right? Do I need to add the end L? I think I need to add the end L here. C out and L, right? Because it doesn't end it here. So here, C out and L. I need to use those and L's. Okay, so check this one out, right? So you see, this is the original one. This is what we have. And okay, this 5 was removed. And this 5 was removed, right? It's after the 23, before the 7. But this 5 is kept, right? And the 17 is there. But didn't we have only one 17, right? Like you see, remember we had only one 17, right? So it looks like these ones are the duplicates, you know, here. Like 3, 5, and 17, these are the duplicates of what we have removed. And check this out. We removed the 3 5s, 1, 2, and 3 5s, right? So what happened over there is like the elements were shifted, but the ones that were in their place, they're not erased, right? So we're kind of having the duplicates. So probably it would be better to say that I have like this new end over here, right? I wonder if it works. This new end. Let's see. Copy it. It doesn't want to accept it. What does it say? No instance of function copy matches the argument list. It somehow doesn't like my new end over here. I have no idea why, to tell the truth. Because this is an iterator. So the remove, let me hover over it, right? Remove. Okay, so remove returned me the iterator, right? And in this case, it's, oh, okay, so this is what I didn't like, because I had the C begin here, and they didn't play out together because this was const iterator and this was just iterator. So that's why I didn't want to work. Okay, so let's try this one now, right? Aha, okay. So this is now a new ending then for the vector, right? So we kind of discounted those elements from the consideration, right? Okay, so you see what I mean? When you know and when you remember about some algorithm, you could find the information, you could look it up, you could use it, right? But your background here is built on the things that we kind of go over, right? So you remember that, hey, there was something like that. So then later on, even if you forgot the syntax completely, you know, you could go Google for it, look into the reference and find how to use them. Okay, and you will probably remember, oh, there was something like tricky about that method. Let me read everything, you know, in the description carefully. Okay, so this is the next stage. Okay, and I need to mark, like, because I have my notes here. What have I did? What should I do? So we did this one, we did this one, and we did this one. Okay, now let's use the find method, because I promised in the lecture slides. So the find method is funny. It returns the iterator to the location. You know, and sometimes who needs that? Why don't we get an index, right, of that location where you first found it, right? So the find returns an iterator. Do you see it over here, right? So the first, the last, and what's the value, and then it returns the iterator to whatever type of the element is, right? And let's copy and paste. So, I mean, we could, I would comment this out because we are removing something here. So let me comment this one out so that the original array will be still in place, right? Like this. Okay, so now since we are looking for things, I could definitely use the constant iterators, right? And then what tell you to find? Let's find 45, right? Why not? Let's find 45. 45, okay? Now, once again, let me say auto, because, you know, once again, I don't want to like guess or do some things. Let me just say auto and then location. Well, as it will turn out, it's not a location, right? It's a value. So what I will do is, no, let's do this. So once again, I already know that it's an iterator. So if location is not equal to my VC, okay, and, right? So if the element is indeed found, right? If the element is not found, the function will return the iterator to the end of the vector, okay? So find returns iterator to the element if it is found, otherwise to the end of the vector, right, that we have. Actually, after the end, right, after the end, to the after the end, right, like this one. So the end shows, to points to after the end. Okay, see out. 45 is found in the vector, right? Like, congratulations. Something like that. Now, we do know that it's there, so I don't need to put the else statement. However, I just want to show you, is it a location, right? The question mark, because I'm going to see out the value. Now, the value location, it won't let me to see out, right? So no operator. So I will dereference it, right? And you will see that it will be pointing to the value of 45. So it will not be pointing to its location. Come up, come up, come up. Yeah, so you see, so 45 is found in the vector. Is it a location? No, that's definitely not a location. Location of 45 is 1, 2, 3, 4, 5, 6, 7, 8. Okay, minus 1, 7, right? Okay, so it's a 7th position. It's very inconvenient, right? And we don't have the index. So if you try to index algorithm, we don't have the index. But try to find what function will, what algorithm can help you with the position of the element, right? So what position the element is at. Okay, so now this one I did. What do we need? Okay, find if. Now let's use the find if. Find if. Okay, so as you could see, we also have the first, the last, and then the predicate. The predicate is a function. What does it satisfy to, right? So this find if, find the first element that satisfies to the predicate that will be given as a third parameter here. It will be unary predicate, so it takes only one parameter, right? Function. So finds the first element that satisfies, right, to the unary, so it takes only one parameter. Predicate. Now, predicate, you remember the discrete math, right? You studied the logic there, like the first order logic, you were talking about the predicates there. It's like functions, right? Predicate. Okay, so predicate. Predicate function. So we will check for what? What do you want to check for? Let's check if we have a number that is greater than 30, okay? Or greater than something. It's like, greater than 30. Yeah, 30. So it should find the 45. 45 will be the first one that satisfies it, right? We will check if a value is greater than 30, okay? So find if my VC begin, because we're not going to modify, right? My VC end, and then the predicate function, right? So that will be a lambda. So we could use the lambda here, right? We could use a function here, but I'll show you the example later on today. So now, lambda, like this and like this, got it, right? Like this, right? So 3 elements of the lambda. Okay, so we are not going to capture any variables, but we are going to inherit auto item, right? So item will be provided by this. Now over here, we will return true if the value is greater than 30. So if, okay, okay. So if item is greater than 30, we will return true, right? We will return true. And if it not, oh, you know what? Ooh, we could make it much easier. Just let me think about it. No, we could do it easier. We could just say return item is greater than 50, because I was going to put the else statement, right? The else statement I would use to say that if it is less than 30 or equal, then I should return false. So I do have always to return an answer, whether it's true or false, right? But this one actually minimized the amount of work for me, right? So check this out. I am getting this item from this range. And what I do is I return the Boolean value, right? The truth value of the statement that the item is greater than 30. It's much more compact. It's much better, right? Than what I could do. So find if. Okay, the first element. So it also will be like a location, right? So auto location. I already had it. Let's do lock. I don't think that there will be any issues with it because it was already established over here. So once it's set, it's set. But let me do another variable here. And let me move this one to the next line so that you could see it nicely. Okay, so auto lock. Now, since we know that it's there, right? Let's just keep it simple. What is it? Lock or whatever whatever element is greater than 30. Is the first element greater than 30? Like this, right? So since we know that it's there, let's run it. Oh, and hopefully it will work. Oh, syntax error. What have I forgot? I know what I have forgot. You remember I told you I forget to put the semicolon here all the time? That's the thing. So return is a statement. It must be finished with the semicolon, right? And I'll tell you once again why it happens, because we have these, right, constructs over here. So that's why we tend to forget, unless we write it 30 or 40 times, and then we'll be like automatized. Okay, so you see over here what it says? 45 is the first element greater than 30. So we have it over here, right? Okay. Now, once again, all of this could be done with the things that we did before, and we would even be able to give the location, right? But we are exploring the things that we have in our repository of the algorithms. So just bear with me for this class. Okay. Now, this one I did, sorting. So next item is sorting. Sorting we did before, it's so easy. We will do, what is it? Oh, we are going to modify, right? So my v dot begin. I'm going to modify it, so I cannot do the constant iterators. My v dot end, and that's it. So after it, it's sorted, right? So what I can do is I could print it. See out the vector sorted, right? Okay, and we will do that copy again, right? The copy from here to here, the output, and I can easily do them constants, right? So sorting, printing it out, and you know, wait, what did I do? And you know what? We are going to use it for the binary search. You remember we had the binary search appearance before, and I said that, hey, you know what? For the binary search, we need the elements to be sorted. So that's why I want to use the sorted, because I remember that the next item I do is the binary search. So, but just to see that it's sorted, it is sorted. 5, 7s, 9s, right? It is sorted. Okay, so just don't forget to add the C out and L at the end. So now let's do the binary search. Using binary search. Okay, I don't know if you've covered it before, the idea of the binary search. Let me run the program again. What the binary search does is it splits the array into halves always. So this is the binary search idea. Hopefully, you had it before, but just to remind you, it starts with the middle element and it compares it with the one we are looking for. If they're equal, it returns you either the true or the position of the element, like, depending on how the algorithm is done. But it returns you a positive result. If it is not equal to it, then it compares the element to this middle element. If the value we're looking for, target value, is greater than it, then we will be running the binary search on this half. And if it is less than the middle value, then we will be running the binary search on the left half. And very often we exclude the middle element because we already compared to it, right? So we want to minimize the amount of work and so forth. So the binary search algorithm is called, right, on the half and then on another half and on the other half and so forth. So it works faster than the linear search in general, right? And in CSI 3, you'll be comparing their running times. So, okay, but binary search, you see this one, right? So here is what it returns. It returns a bool, right? If the element is found. So first, last, and what are we looking for? Okay, so we could use if, right? So if binary search returns it, then see out the value of whatever it is located. We'll decide what are we looking for, right? Okay. And then else, see out the value of whatever it is not found, right? Okay. Something like this. So let's do the binary search. We'll do this, right? Because we are not going to modify it. Did I overdo the parentheses? Yes, I did. Okay, here. So comma, and what value we are looking for. So let's find the 7 first, and then we'll find something that is not there. Value of 7 is not found, right? So if it is found, it will return me true. Okay, I'm missing the parentheses. Here, the second parenthesis one from the if condition, right? It's like this, probably helps. Okay. The value of 7, okay, the value of 7 is located. But if I would, for example, look for 30, right? The 30 will not be found, right? And we will get there. The else statement, right? So the value of 30 is not found, something like that. Okay, let me see what else on my list. Greater than. Okay, so yeah, you know which one? The none of function, the none on function. It's an interesting one. And what we will do here is we'll have our lambda expression defined separately. It's like, we'll associate it with the variable. It's very interesting example. So let me do none of. Okay, so here is the idea, using none of. None of determines whether none of the elements satisfy the predicate function that we will be given, right? So whether none of the elements satisfy the also unary. So it takes only one parameter. Unary predicate function, right? Now, what we could do there is we could determine whether we have elements, like the example, I think the book used greater than 10, and I want to use greater than 100, okay? So let's determine whether the vector has any elements greater than 100. Now this example is very nice because in order to keep things compact and nicely and clearly readable, we have to use our lambda expression outside. And we could use it in the non-off, but I remember that in my screen it was like pretty big. We'll see it right now, the demonstration. It was pretty big, so it was like really wrapping over. So this is our lambda, right, that we will be using. This is the body of the function, right? So we will not be capturing anything from our function, but we will be using one parameter, right? So we will be auto-deducing its type. Now, what we would like to return for this one, determine, it's okay, checks if the value of the item is greater than 100, right? So 100. So what we will do is we will return item is greater than 100, right? Now, it's very similar to what we had before, right? The value of 30, like, something greater than 30, right? The first element greater than 30. But here we are talking about all elements being less than 100. So this function checks whether it is greater or not. Now, what I can do with it is I can give a name to it. So, for example, is greater than 100, right? So I'm giving a name to it. And since I'm giving a name to it, first of all, I have to put the semicolon. Secondly, I need to know the type. And since I'm lazy, I'll do the order, right? So what I did over here is I created a variable and I initialized it to be the lambda expression. So it is referencing the lambda expression. And I can use it later on inside the non-of, right, as a unary predicate. So watch me doing it, do it. Non-of. So once again, 3 parameters. Where is the C begin, C end? Okay, and then just the name. Just the name. So this is something that we called function pointers, right? Function pointer. So I'm not using the parentheses here. I'm not calling it. I'm giving the link, right? The pointer to the function. In this case, it's a lambda expression, right? So none of. Okay, I'm calling it, and let me check if, right? So if none of the elements will be greater than 100, right, then I will say all the elements of the vector are less than 100. And since I do expect to see it, right, because none of the elements were greater, I won't put the else here, but I could, right? I could put the else, right? Okay, let me put it. None of the elements are greater than 100, right, like this. Okay, this is the last one. Okay, so all the elements of the vector are less than 100. Okay, so that's another play with the lambda expression where I did define it separately, because what I could do is I could, of course, put it over here, right? But it's kind of too big, so I'll have to do it on the next line and so forth. And I also wanted to show you that we could use a variable, right, to associate it with the lambda expression. Okay, so this is it with the algorithm so far. So once again, you will be seeing another bunch of them in the textbook, but I also wanted to discuss another topic. It's a replacement of the lambda expression. It's a replacement of function, which I, by the way, didn't show you yet. I'll show it in the last example. So it's another thing that we could use. Fortunately, it will involve the template class. I'll have to do it. But, anyway, let's do it because we will be seeing, I think, a little bit of the template classes. You will be working more on them later in CSI 33. But we will see just a tiny bit of them if my memory doesn't fail me from our plan of lecture, of class meetings. So let me jump for a moment. I think I have only one slide. I wanted to add more, but I didn't. So it's like, one slide, but it's, like that. So it's about the function objects. Function objects. So the standard library algorithms usually accept lambda or function pointer, which I didn't use right yet. You'll see it in this example. And the binary search algorithm, which we just used, we used it with the 3 parameters, right? But it actually has the optional 4th parameter or argument. It's a binary predicate, binary, so it takes 2 arguments, the search key and element from the collection. So the function returns true if the search key and the element are equal, right? And false otherwise. So what it does is it gives us an opportunity for this algorithm of binary search to be applicable to the collections or the containers where the operator of comparison is not provided for the elements of the collection. So it happens and it gives us this flexibility, right? The need to have this binary search for argument. So any algorithm that can receive a lambda or a function pointer can also receive an object of class that overloads the function call operator. This function, it's named operator parenthesis. It's a function call, right? But it's always associated with the class, right? With the object of the class. That's exactly when we might need, right? The binary search for a parameter. So an object of such a class is called the function object. So this, and so the object that has this operator, right? So, and it could be used like lambda, like a function or function pointer. So it's an interesting example. It's very useful in some situations. We don't get a demonstration of why do we really need it. You only get the technical details about how you can do it. Okay, so once again, this is like the suggested assignment, not for grade, it's only for practice, you don't need to submit it. And only first part of it, I wanted to come up with something for the lambda. But let's go and look at the example for the function objects. So once again, this program kind of will show us all 3 examples, the lambda expression, the function, and the function object, okay? So once again, I do have a small draft of, me doing something there. Remove. And what I did actually is I played with the C style arrays. I will remove it. We'll work with the vectors because they're so much flexible. Existing item, where was it? I think this one, function object example. Yeah, this one. So what I did over here is I played a little bit with the C-style arrays and with the accumulator function. So the idea is following. Let me remind myself. We would like to accumulate the sum of all the elements in a video. Okay, so that's what we will be doing through all these 3 examples. So just adding them up, right? Accumulator function. So we have this accumulate algorithm. It's mentioned over here, which takes, once again, the beginning iterator, the end iterator, and then the value to start with. And it accumulates all the values in, in the result. It returns it with the 3 parameters, and it adds them all up to the 0. So if I put some other value here, it will start with this value, right? So check out how did I work with the C-style array. This is for the output, right? It's the standard thing that I had from the previous example. And this is just to move it to the next line to kind of make sure that we have some space there. I could remove it. This is what I do with the copy. So you remember that the A is the pointer to the very first element in the C-style array. And if I say the A 10th, it's after this value, it's after the 10, right? It's, it's nothing, right? And I get the reference to it. So this is how I could work with the C-style arrays and use them as iterators, because these are basically pointers. So they could be converted to the iterators with no problem. Okay, so here I am displaying all the values, and here I'm using this function accumulate, right? And similar to what I did in the copy, I provide a clear reference. I cannot do them as constant, right? So they, they are the ones that allow modification. So something like that. So if we display it, right? If we display it, that would look like this. And this is, I would say, like, it's one of the easiest ways to use like the lambdas or whatever. We are not using the lambdas, we're using the algorithm here, right? The accumulate function over here. So let's go over the examples with the accumulators, and I'm going to replace this with the vector. Okay? So I'm going to include vector, and I'm going to say that I have a vector of integers, and I have the name, again, my v, I like it, and then some values. I don't need to worry about how many elements are there, just as long as my fingers are not tired, right? I could put them in. Keep this, comment this copy out, but do the copy with the elements. So we do my VC begin, right? And then my VC end, and then output. So that will allow me to display all of them. And over here, I will do is the elements of the vector. Okay, like this. Now with this ones, I'll remove this one, and I will not use the accumulate for now, and I'll hide the result over here as well. Now I'll move it over here, but this is what I'm going to give. So let me check my notes. Okay, so this is what I will do. I will instantiate the results with the accumulator, but with the 4 parameters. Accumulate with the 4 parameters. So I'll copy these 3. I'm not going to modify them. I'm starting with the value 0 in the beginning. And you see 1, 2, 3, 4th parameter, like reduce operator right here? Well, actually, it will be the function that tells me how the elements are accumulated, right? So 4th parameter, function that tells how the elements are accumulated. Okay, something like that. So here, I'll do a lambda expression for now. Oh, you know what? No, I have planned the function. Okay, so this is my function. Sum of, what about the squares? Let's do the squares, because the book used to do the squares. We could do the cubes, like when everything. Let's do the squares like the book did it. Sum of squares. Okay, so I'm not going the lambda yet. I'm giving the function name, which is not present there, right? So I'll have to define it. So what I'll do first, that's what I promised you in the very beginning, and I didn't do it, but I will do it as a function, sum of squares. So int sum of squares takes 2 parameters, right? Takes 2 parameters. It takes the total and it takes the value. Now what it will do is it will add the value squared, value plus value squared plus value to it, and I think we could return it. Yeah. Okay, I won't add it. I'll return it. Return it. I need the return for this case. Return total plus value times value. So what the sum of squares does is it grabs the total, whatever I have, and it adds the product of these two functions, two values to it, okay? We're working this one, got it like that. Okay, let's try it. See out the sum of squares of all the elements is results. Oh, okay, something like that. Let's try if it will work. And did you see that I did not provide any parameters? Do you see it? I did not provide any parameters, right? So what happens over there, and let me pull up this again, is that the accumulate function sends them to the sum of squares, right? It sends the 0. So according to what we see, it's the first value right there. And then it sends the element from here into it. And it looks like these two parameters kept changing, right? So the result of this function was sent over here. It's kind of the hidden recursion here, don't you think so? It's like a hidden recursion that we have here, right? Because the result of this call is sent over here, right? So for the next item that is being called, we have a new value here, and it will be supplied to the sum of the squares as the first parameter, and this, the next from here will be supplied to this one. Weird, isn't it? It's like really weird. But that's how it works. That's how the accumulate function works. So, and it's one of those algorithms that I didn't cover in the previous examples. Okay. Now I don't like it here. Let me add the C out here and out. Okay, so that it will be on different lines. So this is the example where I defined a function and I used its name as a pointer because the name of the function is a pointer to its body, right? Now, this is another option. This is when we will be using the accumulator function, right? Let me see. Yes, I do have the accumulator function next. Okay, so I just want my note to be closer to me. Okay. So let's think about this. We'll also use the accumulate, and we could also use the result. Should we change it? Yeah, like we'll just change the value. So accumulate. And then the same beginning and ending. Okay. And then our lambda function, right? So it will be this, this, and this, right? Okay. Now, what am I tying over here? What am I tying over here? Probably nothing. Like I could think of tying the result in, but I, don't think that I will need it. So this is what we will do. We will use two parameters here. So we will do the order, right? The order total, the order item, right? Accumulate. Yes, I wrote it correctly. I think I forgot to put the semicolon here. That's why it's still, okay. Hopefully it will be okay after I finish, right? And then what we will do here is the statement of this function, right? What did it do? It returned, let's do this. But I will replace the value with the item. And item. Okay. Oh. Did I forget the parameter here? The 0? I think I forgot it. Right? I forgot that 0 here, that we are starting from it, right? Okay, all of the errors are removed. Let's try it. See out. The updated result, right? Result using a lambda expression. Result and L. Let's try it. Do I have error messages? No. Okay. Yes, the result is the same. 61,846. Yes, the result is the same. So whether we used, move it a little bit, the function, or whether we used the lambda expression, the idea seems to be the same, right? So two elements are provided by the accumulate, right? The total over here, and then the item over here, right? Okay, now the last example will be with the object. So in order to do that, I need to announce a class. I need to announce a template class. So some of the syntaxes here will be a little bit new to you, and something will be, similar to what we had before. So I'm saying that I'm going to have a template. Type name, let's see, T, right? Quite often is used. And then I say class. And then I will do sum of squares, sum of squares class, right? Now, the definition here of the class will be very similar to what we had before, with one exception. We don't need a lot of things here, right? So we won't define the constructor. What I need to get from here is that operator parenthesis, right? This one, operator parenthesis. I need to redefine it, right? Now, it is a template because, who knows what will be provided over here? What if I'm working with the double values, right? What if I'm working with the strings? So that's why I have to do it as a template class. Okay, so the value of the result will be the T, right? And then this is the operator's name. So now here comes the arguments list, right? And here what we could do is we could use the T ampersand total, right? And then we can use the T ampersand value. We can even make them constants, to tell the truth. Definitely this one, constant. But I'm pretty sure this one we could do constant because we are not modifying it. Let's try it. Okay, now we are returning the same thing as what we have over here. Total plus value and plus value here. Okay, so the function works in absolutely the same way, right? It's just here I had to define it as a template, and there is no other way for me to do it if I wanted to be working there. So I have to do it as a template function. Okay, so type name T is the return type, T is the total, and T is the value. I think we are good here. Okay, so let's go for the modification. I don't think that it's gonna be that much different. Okay, now using function object. Okay, so here, this one, using lambda, right? It's like this. Okay, so let me copy. No, I'll copy this one. This one is easier to modify. I'll just copy and paste it because everything over here is the same, right? The only thing that is different is that I'm just updating it, and over here, what was my object name? Here, sum of squares class. Sum of squares class. So it's a template, so I need to, announce it on what? That it will be on the integers. And then I need just an object of it, right? So, I just want an object of it. So I could do either this, right? Because it will create an object for me. It doesn't have a name, right? So I could either do this, or I could do this code when I create it first, like I give it the name, something like this. Over here, I could do like this, and then function object, just give it a name, right? And then I could provide this name over here instead of this. Okay, so then I could do this. That's another option for me if I, I'm in favor of doing things like separately, like this. So this could be also done, right? Okay, so what I mean here is I need to create the object that has this operator defined there. That's it. I don't need anything else. And unfortunately, this is the only way to do it. So of elements via function object, right? Is, and it's this one. Okay. Let's try it. And I will let you go after we finish this. I know that it's already, how much? 37 minutes. Okay, so it's the same value over here that we have. Oof, we use this function object here. The only way to use it here was that if we define the template class, the only thing we needed from it was the operator call function, right? It's the call function operator. So that's the one that we needed, which behaved exactly like the sum of squares before, which behaved exactly like the lambda expression, where is it, over here that we have, right? So all three different ways of doing the very simple stuff, which we could do with the for loop, right? But once again, just, bear with me on this one. You might not be using it, ever. But if you will be coding in C++, most likely eventually you will run into these items. Okay, so let me stop the